And good evening, AP Physics students. Hope you had a good break. Mr. Kirsten coming at you here, talking about electric field lines today, electric fields inside conductors, and going to look at example problem 29 from chapter 16. So let's talk about electric field lines a little bit. So what's difficult about electricity and magnetism? Well, there's these things called electric fields, and we can't really see them, and we're not really familiar from them from everyday life. So we got to have a way of imagining them or looking at them. So we came up with electric field lines, and they're just arrows that do a couple of things here. What do electric field lines look like? Here's some examples. Well, electric field lines do three things. First of all, they point in the direction of the electric field. All right, electric field lines point in the direction of the electric field. That kind of makes sense, right? Okay. So I've drawn some electric field lines up here. What direction does the electric field point in this region of space? Well, it points to the right, or in the positive x direction, maybe. And remember that the electric field points in the direction a little positive test charge would experience a force in. So if we had a little positive test charge up here, it would experience a force to the right here, or in the direction of the electric field. Okay, so another thing about electric field lines is that the field strength is proportional to the number of lines. Okay, field strength is proportion. Oh, spelling so hard. To the number of lines. Okay, so this is an electric field. How would I draw an electric field that's twice as strong in this region of space? Well, I would draw twice as many lines. Okay. So if you have more electric field lines in a region of space, that means the field lines are stronger there. All right, twice as many lines means twice as much. The magnitude of the electric field is twice as much, maybe 20 newtons per coulomb instead of 10. Right. Also, electric field lines start at positive charges and end at negative charges. So start at positive charges and end at negative charges. So to illustrate this here, let's do a little example here. Let's imagine that I had a positive charge Q, and some distance, say L away, I had a negative charge that was 3 times as big, so negative 3Q. What would the electric field lines look around these charges? Now, there are actually many correct answers we could come up with here, but we're just going to come up with one. So I'm going to start out, okay, if I had a little positive test charge right here, what direction would it point? What direction would it go? It would go that way, right? So electric field lines point away from positive charges. You might say that they originate at positive charges. Now, if I had a little positive test charge right here, by the way, what do I mean by positive test charge? It just means it's a small charge, not big enough to change the electric field around it. Okay, so if I had a little charge here, positive, it would want to go this way, and here it would want to go this way, here it would want to go this way, here it would want to go this way. So this is kind of a start here, and then we can kind of start to imagine what the field lines would look like in between here. Now right away, I want to notice that this guy has 3 times the charge as this guy. So I need 3 times as many lines surrounding this charge as I would surrounding this charge. Now, field lines normally don't just end. They end at negative charges or maybe at infinity. They go off the page. But let's start to think about, like, if I had a low positive test charge and I was right here, what way would I go? Well, I'd be repelled by this guy. I would be attracted to that guy, so I might go this way. So the field lines should really point, say, maybe this way over here. So if I do this at a number of places, I could probably see that the field lines would actually curve kind of towards the negative charge here. All right. So this guy probably goes off and ends at infinity. These guys kind of curve in. These guys curve in. These guys are coming in from infinity. All right. So that's an example of what field lines might look like around a charge distribution like this. And that was problem number 29. Okay, nice job so far. Two quick things here about electric fields and conductors. So what is a conductor? A conductor is like a metal, okay? Something that conducts electricity very well. And why do they conduct electricity? Well, the electrons are free to move around. And because of that, the electric field inside a conductor is always zero, at least in static electricity. When dealing with electrostatics, I should say, is always zero. Why is that? Well, if there were an electric field inside a conductor, the charges inside of it would be free to move around. And they would move around in such a way as to cancel out the field inside there. So the electric field inside a conductor is always zero. Second thing we want to know about electric fields and conductors is the electric field is always perpendicular to the surface of a conductor. Right? And we'll talk about this in class a little bit, but these are two things you want to know about electric fields inside conductors and at the surface of a conductor. All right, nice job, physics students, for your fun time end of video thing here. I have two funny things to show you. These are a little bit of Jefferson history here. These are Mr. Kirsten's old really old student ID cards. My mom was cleaning out some things over the holidays and found these and gave them to me. So there you go. Notice the long flowing hair here, of course. This really shows through well on those. So, whoo, fun stuff. All right, we'll see you in class tomorrow, physics students. Nice work.